when they ask us for the cross product, understand what they're asking for is a vector that's orthogonal to the two given vectors. So if I have u and v, I'm looking for this third vector that's orthogonal to both of them. Now that's written in 3D. This will be u cross v. So how do we find this mechanically? Well, u cross v is going to be different than v cross u. The cross product is not commutative. It looks like multiplication, but it's not. So 4 times 3 equals 3 times 4. That's multiplication. That is commutative. The cross product is not, so be careful here. If you do u cross v, make your 3 by 3 matrix, I, J, K, and I'm not just kidding. U, if you're doing u cross v, u, now this is 1i plus 2j plus 1k. The components will be 1, 2, 1. Please remember that this I is not the I from a complex number, a plus bi, where I is the square root of negative 1. This is a unit vector in the direction of the positive x-axis. So this is the vector 1, 0, 0. J is a unit vector in the direction of the positive y-axis, which is 0, 1, 0. And k is a unit vector in the direction of the positive z-axis, which is 0, 0, 1. So just be careful of that. So if you're doing u cross v, we're going to go 1, 2, 1, and then v will take the third spot in this 3 by 3 matrix. 3, 1, 2. 3, 1, 2. And I am now going to use my little ditty. I say, if I want the i's, and I do, this vector is something I plus something j plus something k. I want the i's. I say to myself, if I want the i's, then cancel the i's. What do I mean by that? Here are the i's. I cancel the i's. I put my cute little hand over I, and I'm left with this 2 by 2 matrix. 2, 1, 1, 2. 2, 1, 1, 2. That is my I. I canceled the i's, and I was left with that. If I want the j's, guess what? I cancel the j's. So I put my cute little hand like that, and I get 1, 1, 3, 2. If I block off the j's, I get 1, 1, 3, 2. 1, 1, 3, 2. And that will be j. And if I want the k's, I'll cancel the k's. If I cancel the k's, I get 1, 2, 3, 1. 1, 2, 3, 1. And that is our k's. Now, we're going to add that one. This is where students go wrong. Everyone can do this, except please be careful here. We're going to add that. I'm sorry. Please be careful that. Do as I say, not as I do. We're going to subtract this. That's the problem. Students forget that we got to subtract that one. Now we treat each of these as a 2 by 2 matrix, of which each, I don't know, each of which we must take the determinant of the 2 by 2 matrix. Remember, what I say to myself is down products minus up products. I'm going to go down minus up. So in this case, for the i's, I'm going to say this is 2 times 2. That's cross down minus cross up. Minus 1 times 1. Those are the i's. Careful, careful, careful. This is minus. The formula calls for us to put a minus there. Our down products minus our up products will be 1 times 2 minus 3 times 1. And those are our j's. And then we're going to add in our down products minus our up products. That's going to be 1 times 1 minus 3 times 2. And those are our k's. This is going to be 4 minus 1, I, minus, careful, 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 it's nuclear. Got to be very careful with this. This is going to be 2 minus 3, j, plus, this is 1 minus 6, k. And when we simplify, we get 3i, careful, 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 minus negative 1j plus negative 5k. So ultimately we get 3i plus 1j minus 5k. I was looking for my ijk. 3, 1, negative 5. And I think I found a vector. I found a vector. I think I found a vector that is orthogonal to the two given vectors. How could I test that? Well, my new vector, 3, 1, negative 5, I could dot it with my original u, almost like a maternity test. I think this is the mother. If the dot product of this and this is 0, which it is, then I have found a vector orthogonal to u. And here's the big one. Is it also orthogonal to v? Well, my resultant vector from the cross product, 3, 1, negative 5, if I dot it with my original v, take my new vector and dot it with v, I should get 0, and I do. So we're happy because we found a vector that's orthogonal to both. That is u cross v. Now, what if I changed the game a little bit and I said find v cross u? Same situation as we had before. We're so happy we found it. We confirmed that 3, 1, negative 5 was our u cross v. I told you u cross v is not necessarily the same as v cross u. Finding the cross product is not commutative. So let's find this. I, j, k, v cross u. Well, v now gets in this second row because we're doing v cross u. And 1, 2, 1. V is 3, 1, 2. That goes in the second row because I'm doing v cross u. Now u goes down to this third position. So if I want the i's, cancel the i's. I get 1, 2, 2, 1, I, minus, don't forget, if I want the j's, cancel the j's. That's 3, 2, 1, 1, 3, 2, 1, 1, and that will be j, plus, if I want the k's, cancel the k's. So it gives me 3, 1, 1, 2. 3, 1, 1, 2. Those of you who are future accountants will do very well here. You've just got to keep track of all your numbers. None of it is hard. 1 times 1 is 1, minus 2 times 2. 1 minus 4 is negative 3i, minus down products 3 minus up products 2 is 1j, plus down product 6 minus 1 is 5k. So I get negative 3i minus 1j plus 5. What? Look at that! My original u cross v was 3, 1, negative 5. So here is v cross u. Let's compare that to u cross v, which we got 3i plus 1j minus 5k. Holy cow! They're the same vector, but in opposite directions. So if this is u cross v up here, guess what? This one is v cross u. It is, in fact, orthogonal to both of those vectors, u and v. It's kind of on the bottom side. If this is the surface of the water, this one's going up to the sky, this one's going down to the bottom of the ocean. Both vector u cross v and vector v cross u are orthogonal to the original two vectors. How can we test that? We could find our new vector v cross u and dot it with each of the original vectors, and we'd see that the dot product is 0 to confirm that, yes, we did in fact find a vector that's orthogonal to the two vectors. Could you just find u cross v and then change the sign of each of the components to find v cross u? Sure you could.